Hi everyone and welcome back to the multiverse of 100 plus data science project series. In this video, we will build an image data compressor using an unsupervised learning technique called the principal component analysis, also called the PCA. So let's begin with the basics of image data. So you are probably familiar with the fact that the image sent to the chat platform like the WhatsApp. So when you're sending any images by the WhatsApp to the user number one to the user number two, it will automatically reduce its size. Let's say I have one user, let's say user number 01 is sending a picture to the user number 2. Let's say user number 2 by the WhatsApp or the messenger. Okay, let's say messenger. Okay, messengers. So let's say I'm going to sending here on images. So it's nothing but let's say 2 MB. So when I send the images by the WhatsApp or messenger, it will automatically reduce its size. Let's say 1 MB. Okay. So this is to save the internet bandwidth as well as it will save the storage space that is used by our mobile phone as well. Storage space. So some website even produce some of it actually website even offer you to produce this kind of similar or same kind of images with the same email file size. So but how exactly actually they do that? Okay. So the question is now the but how exactly they do that? Okay, they do that. So you will explore these questions in greater detail, but let's first see how computer actually read the images. Okay, how computer read the images, read the image data. That you not also learn about that, right? So if you have the basic knowledge of OpenCV or the computer vision tactic, you obviously know that how the computer actually read the images. So you know that computer read an images as a matrix. So okay, as a matrix. So computer read the images as a matrix. So let's say as a matrix. So this matrix actually holds some kind of pixel value, and this pixel value represent the color. Okay, this pixel value represent the color. That's a color. So our maximum color is nothing but the 255, which one stand for the white, complete white, and the minimum value is 0, which one is completely black. Okay, so how you try to explore any kind of images, or you wanted to print it, you may get here minimum value as a 0 and maximum value is a 255. So this is how the actually the matrix is contained in the below. So this matrix is contained three dimensions. One is for the height, sorry, not height, actually height, as well as it has the weight, and also have the number of channels. I mean, how many channel it have. So if it is a RGB image, it has a 3 channel. So if it is a grayscale image, it's nothing but the 1 channels. So RGB means the red, green, and the blue. Red, green, and the blue. So this is containing the matrix as well. So based on the number of channels it present, we can classify the image into two types. One is RGB, another one is a grayscale image. So in the case of grayscale image, it can deprecate it in matrix with the pixel value just 1 channel. Okay, just 1 channel. So you can say 1 channel, and in the case of the RGB, it has a 3 channel that you can see. So let's say I have one image called, let's say 1024 cross 1024 cross 3. So this is one RGB image. So you have the channel as a one. So that means this is an grayscale image. Now the question is, how can we actually compress the image? So you can compress the image using here an formula or using here a technique that's called the quantizations. Okay, let's say QUNTIZATION. Okay, quantizations. So I'm going to taking here examples. So let's say I have one image with having some shade. So as you know that in our images, it's represented as the 8-bit. Okay, 8-bit. Okay, it represents the 8-bit of the shade. So that's mean the image should be consisting between this 0 to 2 to the power 8 minus 1. That's means 0 to 2 to the power 8 is nothing but 256 minus 1. That's a 0 to 255. So 0 represent the black and 255 represent the actually represent the actually the white. I mean complete white. Now the question is, how can we do the quantizations, or how can we compress the images? To understand it better, suppose we replacing to odd pixel. So let's say I have some kind of pixel, because you know that in the images it's nothing but it's nothing but in the form of matrix, and in this matrix it represents some kind of pixel value, and pixel is nothing but the colors. Now let's say I have some kind of pixel. Let's say I have some odd pixel. So let's say I have some odd pixel. I have some odd pixel. Let's say I have pixel, let's say 1 comma 3 comma 249 or etc. Okay, this is my odd pixel. Now with this next event pixel should be 2, 4, 250, etc. Right? So if I if I change the image, if I change the image from the odd pixel to the even pixel, odd pixel to the even pixel, it's not even change the entire things, right? It's not changing the entire things. So we just reduce the memory required to store those values. See, in the case of art, it will taking here more amount of memory. In the case of even, it is not taking this kind of memory. Just you are reducing the memory required to store those values, right? So this is called the quantization. This is called the quantizations. It's one of the simplest way to perform the image comparisons. Now in our case, we're going to using here a technique, machine learning technique called the PCA, also called the principal component analysis. So which one is nothing but one unsupervised technique used for the dimensionality reduction. That's a dimensionality reductions technique. Okay, it's called dimensional reduction. So let's take some deeper to this PCA. So I'm just going to taking here an example. Let's say we have 10 features. We have some 10 features to our data. Let's say 10 features to our data sets. Okay, let's say our data sets. So if I using the PCA, so in that case we can actually creating here 5 picture from the data set. We can creating here the 5 picture from the data sets. Okay, so that can retain the maximum information from the original one. Okay, from the original 10 features. Let's say I have one data sets which one having the 10 features, and I can also do the feature scaling. I can do the feature scaling, or either I can using the PCA. So using PCA, we can also reduce the dimension of the features so that we can have the more amount of informations. Okay. So same thing for this one. Same thing for this one. We can apply to this PCA, and we can reduce some of the feature from that, and we can starting here the important feature to get the information again. Okay. So this is how we can do the image compression using the PCA. Now let's see how can you implementing this one. But before implementing this one, you need to also follow some kind of steps. So let's see what are the steps that need to follow. So in step number one, let's say step number 01. So we need to first, okay, I'm going to copy it from here actually. So first you need to import here some the important necessary library. So let's say import the necessary, let's say necessary libraries in Python, because you're going to be using the Python programming language. Okay. Step number two. In step number 2, we are going to actually read the original image. Let's say read the original image. Let's say read the original image. In step number 3, let's say step number 3. So what you can do in step number 3, we are going to actually compute the principal component for the input image. Okay. So you're going to computing the principal, that's a principal component for the input image. Okay, for the input image, because we are going to taking here one RGB image. So in our case RGB, that's mean it have 3 channel. So you need to also separate them, and for the each of the layer you need to, or each of the channels you need to apply the PCM. Okay, you need to remember that thing, because you're using the RGB image, color image. Okay, so if you're using the grayscale image, just into taking here the one channel from here, and you can easily compute the principal component for the input images. Now the last one is called the step number 4. So let's say step number 4. Let's say step number 4. We can lossless, let's say lossless reconstruction. Okay, reconstruction of the image using a reduced number of component. Okay, that's it. So those are the steps that to follow into building here this image compressor using the PCM. And also one more thing, you know that PCA is actually using the data in the decreasing order, that you have to remember all this thing as well. So what you can do, we are going to collect in here one input image from the person doesn't exist in the website. So it will give you some kind of images. So what you can do is simply going to first generating this one. So let's say the person doesn't exist. Then you can the first thing is appear. You can click on here, and it will give you one images. The person is not exist. If you reload it, so if you reload it, you can see you got some beautiful lady image. So I'm going to save image as, and I'm going to save it to the folders. Okay. So let's save it to the folder. So what I can do, I give it as a test.jpg. Okay. Let's save it. Now it's saved. Now we are going to start our coding right now. So how you do the coding? It's better I can stop my camera because it's taking so kind of competitions. That's why. Okay, so now you're going to explaining the code each and every lines in details. So I will write down this code in the Jupyter notebook. So we have also our images that you can see in our folder that you can see test.jpg. So you're going to using this one. Okay. So first you're going to import from the Python imaging library called the Pillow, or you can say Pil. So from Pil you're going to import here image and the image jobs. So using image, it will actually help us to allowing the opening and the manipulating of the images. And this image ops actually provides some kind of operations like flipping, or you can also do the grayscaling. Okay. And then you import the NumPy. So using NumPy, you can use some kind of numerical operations and image data manipulation and the array. So also imported OS. It's nothing but for allowing interacting with the operating system. Example, you can say that checking the file size or do any kind of operations in the files. Then you also imported the matplotlib. So import matplotlib.pyplot as PLT. So using this matplotlib library, we actually do the visualization. We can visualize the images. Okay. Now after that, what I can do, we're going to creating here functions to analyze the image data. So you're going to creating here functions called image underscore data, which I'm taking here one image path itself as well as the display that you want to display it or not. So let's run in this one first. So it will running this one, it will try to importing all of the module. Okay. Now we can creating here functions called image data. So it will nothing but first opening the images using this image. Okay, that is you already inputted. So image.open, and you're going to pass in here the image path that is coming from the parameters. So this is our original image. Now we need to convert this image into size of KB so that we can reduce the size, okay, in terms of KB. So what I can do, we are going to using here this method called stat, and we passing here this image path, and inside this image path we are taking here the size of the image, and we divide by 1024. Why? Because you know that the gigabyte, or you can say kilobyte, is nothing but 1 MB is equal to 1024. Okay, that's why we divide with this 1024. Now we need to also getting here, we need to retrieving here the pixel data. Okay, pixel data, because you know that the image is in the form of matrix that we already discussed on here. So you can see image is already in the form of matrix, and our matrix is represent in the form of pixels. Now we need to convert them into some kind of pixels. Okay, so it's better I can closing this image. It's not needed at all. Okay, now let's go in the full screen mode. Here you go. Now we need to also getting the pixel data. So using this orig underscore image dot get data, we can getting here the pixel data. Now we need to reshaping them the data into 3D array. Why 3D array? Because you know that in the case of RGB, we have the three things: height, weight, and the number of channels. So this is the 3D data, right? So we are going to store it inside, we are going to convert them into NumPy array, as well as you're going to store it inside these original pixels. Now we're going to checking the shape of that so that we can also store it inside a dictionary. Now I'm going to show it. So if the display is true, then you're going to show it using this plt.imshow, this library, okay, matplotlib library. And after that, you're going to creating here a dictionary, empty dictionary. Here you're going to storing here the image size in the KB as well as the image dimension that you can see. Okay, cool. Now can returning here the this data dictionary. Okay, now let's see. Let's try to running this out. So it's nothing but the JPG. I hope so. So you're going to give here the image path. So test.jpg, and you're going to calling here this image data, and it will passing here this image path. Now we're going to printing here the original data image data, as well as you're going to see the size in the form of KB, as well as you're going to see the image dimensions. So let's running this out and see we got an error or not. Yep, we don't get any kind of error. So we get this image. Okay, we get this image. Test.jpg. I think so. It is hind saved. It saved maybe another images at so. Okay, that's my bad. Actually, when I save these images, maybe it changed it little bit. When I download it, okay. So no problem. You can also use this image as well. So you can see the original image data, and the size is nothing but the 534. It's up to 535 KB, and as well as you can see the shape of the image is 1024 cross 1024 cross 3. Now we simply going to apply here the PCA compose. I mean the PCA compression setup. You can also do that. So using this PCA, we can do the compressions. So let's import it. So from sklar.decompositions, you're going to importing here the PCA. I mean, we are just going to ready our function so that we can also do the compress. Okay. So we're going to creating here a function called PCA compass. So which one taking here an image path itself, and then you're going to load our image path, and then you're going to checking here the pixel value, that you can see pixel value, and then after that you're going to reshaping it because it also reshape them into the 3D array as well. Then you're going to creating here a dictionary for the storing the PCA channels. Now this is the main important part. See np dot transpose. So what it actually do? It will transpose the image array so each color channel can access the independently. See, so you already discussed that. So you have one RGB image, so you need to access it. You need to access it separately. That's why you actually apply here the transpose. That means from the R, you need to apply here the PCA. From Z, I mean in the Z, you need to apply here the PCA. In the B, you need to also apply here the PCA. In the case of RGB images, okay. Then after that, you're going to taking all of the images and you're going to store it inside these variables called the PCA channels. So you can see for I in range image.shape, and you're going to stack the shape. I mean taking all of them, and then you're going to taking here part channels. I mean for R, G, and B separately, and then you're going to convert them. You're going to taking here the number of channels. I mean how many channels each have, and we simply reshape with a single channel image. And then you're going to apply here this PCM and give it here the random state of the 42 so that it not changes every time we run it these shells. And then you're going to using it to feed transform to the channels, the number of channels, because you need to feed it to the number of channels itself. Then you're going to store it inside the PCA channel dictionary. Okay. So here you have our PCA compose file. Okay. So you can run it out right now. Now, if I run this out, so the PCA channel, the PCA compass, we pass the image path. Now, if I need to show this length of this PCA channel, then you can see one more thing. Okay, the channel is nothing but 3 because it has the R, G, and B, and it's a color image. So if you give here any kind of grayscale image, obviously it will give you the number of channel as a 1, number of the channel of the 1. Sorry for my bad. Actually, my connection is lost, even though some of the shell is not running correctly. So that's why I need to run it again from here. So now what I can do is simply going to see our next step. It's about here. The step number 4 is lossless reconstruction of the image using a reduced number of components. So if I see this function, let's say if I go down, if I see this function, it's called the PCA transform that you can see. So it's taking here the PCA channel, I mean the number of channel, how many channel it have, as well as the number of component. Now it is selecting here this number of component. So how can we actually select it? We can select it using here the explained variance. Okay, we can select it by this explained variance that you can see. We're creating here a function called the explained variance. Okay, so using this function we can calculate that how many channels we have, or sorry, how many variance we have. Okay, and how many component we can reduce from here. So for this case, you can pass here this PCA channels and the number of component itself. Then you're going to creating here two variables, one for the variance, the explained variance channels, as well as the explained variance count. So because we have the 3 channels, we have using here actually the three channel image, I mean the RGB image. That's why we're also taking here each of the image and to apply it here. Okay, apply it here the PCA. Now in this PCA channels that is coming from here, it having the number of channel, the red, green, and the blue. Then you're going to calculating here the PCM, and then you're going to append it to this list. So we're going to append it in the form of cumulative sum. So using this cumulative sum, we can cumulating the variance in explained manners. So here you're going to passing here the explained variance ratio from this PCA, because you know the PCA is nothing but a model itself. So here it have the explained variance ratio, and you are going to do the cumulative sum so that we can getting here one cumulative variance explained. And after that we also store it inside this count. Okay, so that we can divide to the number of length. So we are going to store it, let's say variable explained channels, and we passing here the channels and the number of component, how many component you are going to use it here. Okay, so now you're going to calculate here the variance experience. So how can you calculate it? We can calculate with the divided by the number of channels, the number of PCA channels. Okay, then it will returning here this variable expression, right? Now let's run it. Now, if I am running this one with the PCS channel of the 3 and the 1023, which one is nothing but my full the pixel value of the images. So if I see that my original image shape is nothing but 1024 cross 1024 cross 3, that's mean if the image size or the pixel size is start from 0, that's mean the minimum one is 1023. 1023. So if I give it to the all of the pixel value, obviously I can get the exponent variance in the it's nothing but the 100%, right? So if I give it, let's say 800 and checking this one, so you can see got here 99%. That means some of the pixel value is missing from here. Some of the pixel value is missing from here. Okay, that you can see. Now the question is how can it reduce it? How can it reduce it the number of pixel that our image is look like greater? Okay, so for that you can be creating here variables for variance added PC so that you can also see it. I mean, you can print the exponent variance as well. So if I run this code, the same thing that you can see on here, just we added here this y tick, the x tick, and you also creating here the list of the various explanations for each of the channels. So if you're running this out, you don't worry about this code. You can get this code in the description. You can easily access it. So I'm going to calling here this functions called variance this added PC. So you can see for the first iteration, that you can see, it's nothing but up to 60%. You can see up to 60%. How are you actually running this one? Okay. And how the number of step is reduced. You can see here the variance is also decreases. The variance is also decreases. Okay, that you can see. Now the percentage of reduction in size is inversely proportional to the number of principal component is actually used. That you can see variance and the principal component. So you should use the minimum number of principal component if you want to more reductions. If you're using here a less number of principal component, so we may get here some kind of reduction of the size, right? So if I'm trying to plotting this out, as well as this one, this variance that you can see, it is reduced in from after that. Okay. So when I have the number of component is a 9, so I can got here 95% variance. That's it, from my images 95% is reduced. So if I using the 5 as a component, it will reduce here the 90% of the pixel from data. Okay. So if I'm using the 50, if I use the 50 just for the testing purpose, so you can got here 99.13. That's 1% is missing. 1% is missing from my images. So you can also reduce the size of that. Like that. Like that. We can also do that. We can do that. That is actually explained on here. If I actually increase the size, let's say I make it as 100, then you can see it's nothing but 99.60 like that. Okay. You can also increase it, let's say 200. You can say 99.87 like that. Okay. That you can see. So you can see 99.13. So number of component. Okay. If you make it, let's say I just make it as a 9, then you can see it's 95. That you can see 95. If I use it, let's say 5, you can see 92. Okay, it's up to nothing but it's close to the 90. Okay, that's mean when you reduce the number of component, okay, the size of the pixel is also reduced. Okay, now let's try to see these functions called the PCA transform. So using this function, you can reconstruct the images. I mean, get back to it again. So what is happening in this case? In this case, you're going to first getting here a functions called the stamp res. It's a nothing but a list, and then you're going to taking here all of the channels, and from this PCA channels, you're taking here all of the channel itself, R, G, and B, and then you're going to add it to again. You're going to reconstruct the channels, and then you're going to using this PCA components, and you're going to join all the component, and then you can using the dot product in the case of compressed pixel, and as well as you're taking the mean value of that, because mean and the variance, and then you're going to store it inside the stamp res. The stamp res, you append it, and then you're going to transport it again. So transport means you're going to joining here this R, G, and the B channel itself. And then after that, you're going to compress the image. So this function will help us to reconstructing the image. That is, we already separate. We already separate the channels. Now, if you see this one, you can see this is the compressed image that you can see. You can also see it in here, maybe. You can see compressed image.jpg that you can see. Same thing, you can see the size of that, how it is reduced. So you can see dimension is same, and you can see compression percent is 85%, and KB is nothing but 75 KB. Because 75 KB, it will see 75 KB. You can see some kind of dot. You can see some kind of dot. You can see because it will reconstruct in the same image itself. Okay. Now you can testing it out with the another image itself. So you can using here the person doesn't exist. So you can select any image from here. So let's select. I'm going to save the image as let's say download.jpg. Okay, I don't know it's got in here the actual image or not. You can see it's got here another images. That is happening in case of this website. So I can also let's try to uh, reload. Let's try to saving this image as well. Now you can see you may get another image. Let's say test1.jpg. Okay, that you can see. Now you can see another image. Okay, this is an image for the girls. Let's apply it. Okay, test1.jpg. So what you can do, you can go on here, and now let's apply it to the test1.jpg. So you can also creating here applications using the Flux framework. You can do that as well. So let's try to checking this out for this image as well. So you can see it's still running because it will concluding all the things. Okay, that's the images, and after that we may got, so variance is okay, it's less than 45% that you can see. So in case of the variance, you can see you got the 99.9% in the case of variance in these images. Okay, but the first image actually using we got here the 100%. In these images it's working very fine. Okay, you can see 25 number of components 25. Okay, so if I using here this okay, if I using here the 50 channels, it reduced here it in the 97%. Okay, quite big numbers. So you can see some kind of pixel is coming on here, some kind of pixel is coming on here. So and size is reduced, but if I'm going to using here the number of component, the increase the number of component, let's say 70, then 98%, let's say 19. Okay, if I using this one, now you can see this kind of dot pixel is also gone. Okay, try to removing them. Okay, okay, some kind of pixel will actually remove. This is how it actually reduce the number of size. Okay, so you can also increase it, let's say 120. So 99.18%. Now let's see. Now you can see the value is also decrease gradually. You can see on here. So you can see these images, casuals, some kind of the blue dot on here. Okay, cool. So this is how this PCA, the principal component analysis, actually work in case of the image compressions. So that's it for today. Now hope you enjoy this full tutorial and make sure to subscribe our channels and share with your friends. Thank you and bye bye.